Okay. All right. All right. Okay. So good afternoon, everyone who actually watching online and also in this room. And welcome to ETH Colloquium number 17. Okay. So today we have a guest, Professor Nelson Nunes from University of Lisbon, Portugal. Okay. He's going to talk about constraining modified gravity models with gravitational waves. Please join me to welcome speaker. Okay.
Hello.
Okay.
Good
Skin is yours.
afternoon. Thank you. Good afternoon to all of you. For me, it's morning here. Thank you for the invitation, and I'm sorry about last week. Maybe I can share now. Can you see the
You can
slides?
share your screen now.
Uh,
Okay,
yes.
we can see now.
Okay. I think it's working now. Okay. So the topic of this presentation is precisely current and futures constraints on cosmology, F of Q cosmology with LCDM background. This is a report on two works I did with my collaborators, Tiago Barreiro, Bruno Barros, José Ferreira, Tommy Coivisto, and José Pedro Mimoso. So these two papers are here in the slide if you want to know more about it. All right, so as an introduction, just want to revise that space-time is described with two, in principle, independent objects. These are the metric and a affine connection. And with the metric, we can define distances, we can define lengths and angles between vectors. And the affine connection, we use it to relate to nearby tangent spaces. So I have an equation there, of course. I don't know if you can see my cursor, but I'm pointing when I'm sure if you can see. And then with the affine connection, we can define the covariant derivative and also the Riemann tensor that specifies the space-time. The affine connection can be decomposed into three quantities. The first one is the Levi-Civita connection, and the second is the contortion, which is related to the torsion. When we learn general relativity for the first time, we typically put torsion to 0, which means that the affine connection is symmetric. So if you swap the two indices, I don't know, can you see my cursor or not? I'm not sure if I am pointing, you can also see something, or you cannot see my cursor, the arrow. Can someone reply? No? So I'm not sure if you, all right, let's carry on then. All right, so typically torsion is 0, but it might not be. And the third quantity is deformation, which is related to non-metricity. And non-metricity is at the bottom right corner, is related to the covariant derivative of the metric. Typically, when we learn general relativity, we put the non-metricity, or we say there is metricity, which means that the covariant derivative of the metric is 0, but it might not be. And that's the thing that I want to bring. That's what my topic is about. All right. So to have an idea what these things are and what do they do. So when we have the Riemann tensor, it describes how much a vector is displaced, or the direction of this vector is displaced by going through a closed path. So that's what we see in the figure on the left. There's a vector, it goes around a closed path, and you see the direction where it started from is different from the direction where it ended up at the same point 1. Now, when we have torsion, when we have the parallel transport of a vector along one vector, and then the second vector along the first vector, the parallelogram formed by these two vectors and the parallel transport along the other vector does not close. This parallelogram does not close. And when we have non-metricity, we can understand it as a vector that is transported along a path changes its modulus, it changes its size. So this is very interesting, and from these three different concepts, we can actually see that there is a relation between them. if we write an action in terms of the Ricci scalar, the scalar for the torsion, the scalar for non-metricity, then it is possible to show that all of these come about to general relativity, standard general relativity. You can formulate general relativity with these three different concepts. This is very nice. It's very well explained in this paper by Beltran, Jimenez, and Eisenberg. And of course, people tend to extend these ideas, extend this series, and they define the FFR model, the FFQ model, FFT model, because we have the suspicion that GR is not the final history. It's not the final theory of gravitation, because we're finding in LCDM that there are some loopholes. There's some problems. Of course, you must have learned about the Hubble tensor, the Hubble tension, the sigma 8 tension, and some anomalies in the CMB. So it might be that we must look for some extension of general relativity to explain these issues in the standard cosmology model. So in particular, I'm going to look at the case of f of q. So if it wasn't clear, q is the scalar that we can build from the non-metricity, from the non-metricity tensor. We can define the vector and the scalar as well. So it's in the second line. And in Friedman, Lemaitre, Robertson, Walker, then the non-metricity scalar can be written in terms of the Hubble function. So it's 6h squared, and from there we can also write down the Friedman equations, which are these two equations at the bottom of the slide. All right. So there's a slight modification to the standard Friedman equation, as you can see here. And this is interesting. Now, this Friedman equation and f of q in general will lead to two modifications that I'm going to explore. The first one is the evolution in the matter contrast. So you see that the equation for the evolution of the matter contrast, where delta is delta rho over rho for matter and baryons, then we can see that the third term as an f of q. You can imagine these, you can understand these as an effective G Newton. All right, so this is interesting. It was also shown in this paper of Beltran, Jimenez, and Eisenberg. It's not the same as the previous one, but it's another paper on the f of q cosmology this time. The second modification is in the propagation of gravitational waves. So we can have can derive the equation of motion for gravitational waves by perturbing the metric in this way, Minkowski plus a small perturbation, this h mu nu. We have two polarizations for gravitational waves. That's what this A means in the equation. And the thing is, in the f of q models, also in f of r models, f of t models, we have an additional term in the frictional term. So this 2 delta is something new that relates to the f of q. And f of q here, by the way, is the derivative of f with respect to q. And so this modification brings in, as a consequence, modification in the definition of luminosity distance for gravitational waves. So this is no longer the same as the luminosity distance as we use, for example, for supernovae. There's a modification we see in the bottom right corner. There's this f of q today divided by f of q in the past. Right, so the square root of that ratio. So you can see this in Belgasem paper of 2018. So these are the two modifications in the matter density contrast and evolution, and in the propagation of gravitational waves that we are going to explore. And these will help us to constrain the model, and we'll make predictions with gravitational wave observations in the future. All right, so the model we're going to explore in particular is this one, the one that we see at the top of the slide. So f is q plus m square root of q plus a constant. And this is because the Friedman equation naturally allows for ΛCDM, but also allows for something a bit more general, right? So if you didn't have this m is equal to 0, is essentially would be exactly GR with the cosmological constant. But the Friedman equations, I can go back again, right? I can do the Friedman equation. I refer to the Friedman equations. I mean these two equations here, right? With Q equals 6h squared, right? So it allows for a more general expression for F, not just Q plus the cosmological constant, but something else. And this will bring the modification in the evolution of matter contrast here in the third term, 3 square root of 6 h divided by that quantity there, and in the relation between the luminosity distance for gravitational waves and the standard luminosity distance, right? So this is what these are the modifications that once again we are going to explore, and we are going to focus on the case where maybe this wasn't clear, but the f of q that I'm using, the one at the top, allows for a ΛCDM background. So it allows for exactly ΛCDM or something else that is different from a cosmological constant, but in the background is exactly the same, but the modifications comes at the level of perturbations and the luminosity distance as we are seeing. Okay, I hope this is clear. So this is a FFQ model that gives exactly ΛCDM in the background, because we are convinced that we more or less we know what the background is. From all these observations that we have been taking the last 25 years or so, then we can convince ourselves that ΛCDM fits the data very well. And the modifications, if we want to discriminate between different models of cosmology, the difference most probably is in the perturbations, right? Or in propagation of gravitational waves as we are seeing. All right, moving on. So the first thing we did, the first paper we worked on was in the constraints from redshift space distortions, right? So these are distortions in redshift space on when we look at clusters of galaxies. So they seem a little bit squashed because of the gravitational pull of the cluster itself, and how it relates to the redshift from the near part of the cluster to us and the further part of the cluster in the radial direction. So there's from this you can actually extract what is the evolution of the matter contrast and get this relation F sigma 8. So essentially that the data points we obtain is for this quantity F sigma 8, which are this quantity here, and sigma 8 is it measures the power at 8 megaparsec scale. The data is here, the data that we use from Sagredo 2018, and we plot it against the different curves. One is ΛCDM, which is the one in red, and we have our model of f of q that I already shown with c equals 0, which is this dashed line, and the very thin gray line is a model where m is fixed. M gives us the cosmological constant. So this is another alternative model that we used as well and we explored as well. So these are the three models that we're going to compare with each other. Okay, so from here we immediately see that there is this sigma 8 problem, which means that if we fix sigma 8 for ΛCDM, so which is the red line, once again, it seems that it misses the points that are at higher redshift. So the points at higher redshift are above the line for ΛCDM, and for these models of f of q, for the same sigma 8, if we changed m, then we can get a better fit. So this is only by eye. Of course, we did a better study, a better analysis of likelihood analysis we did for these models of f of q, and this is what you got. All right, so these are the results. We have this banana here, this contour, 1 sigma and 2 sigma in the m sigma 8 plane, and you see that when m is 0 is the ΛCDM. So this it's still within 1 sigma of the contours we obtain for the f of q model. The other line that we see here with the red dot with m more or less 4, this is the model where m is fixed, which is the m that gives us the cosmological constant itself, right? And the yellow dot is the best fit for our analysis using a free value for m, and we see that is non-zero. So the data as it is right now, it does not prefer m is equal to 0. It prefers something else, but of course the cosmological constant m equals 0 is still within 1 sigma, as I said before, right? So this is interesting. Other thing is, when you looked at sigma 8 and compare with the sigma 8 that we obtained from Planck, and we look at the plot on the left, this shows what we obtain with redshift space distortions, and we obtain it Planck. Planck is the Gaussian that we see there in red, and in gray is the 1 sigma region for redshift space distortions, and this is the sigma weight we are talking about. So the best values, they don't fit each other. They don't overlap. These two likelihoods do not overlap with each other. They overlap at 2 sigma, perhaps. 2 sigma exactly. Now, in our f of q model, the one where m is fixed, that gives us the cosmological constant, which is the plot in the middle, we obtain the same problem. I mean, actually sigma 8, the best sigma 8 is shifted to 0.9, more or less. So it goes to the other side of the Planck value. And then with the model where the parameter m is free, then it seems that we alleviate this problem, the sigma 8 tension, because now the two likelihoods do overlap at 1 sigma level, right? So of course I'm cheating a little bit, because if you notice, the the width of this plot in sigma 8 is larger for the third model, all right? So the length, the interval is not the same in all the 3 plots. But of course, what's happening here is that as we are introducing a new parameter, a free parameter, naturally the likelihoods broaden, okay? But this broaden sufficiently for the sigma 8 tension to be alleviated. So this is the message I want to convey here, right? So when you compare the several best fit values, either with the chi-square per degree of freedom or the AIC test, then we see that they're all very close to each other. The models are very close to each other. Of course, here it seems that with chi-square, there's a preference for the FFQ model, but a slight preference, let's say. But to the AIC, then there's a preference for the FFQ model where m is fixed as the cosmological constant. But there's a slight preference, but it's not very important, right? So summarizing the first part of my talk, we looked at the model with a fixed m, which has the best fit value for sigma 8, which is sigma 8 is beyond the Planck value. So we also come into tension with the sigma 8 from Planck. The best fit for m when m is free is actually non-zero, sorry, so it's not the same as cosmological constant, is non-zero. And for the model with the free m, the best fit sigma 8 includes the Planck value, so it seems that we alleviate the sigma 8 tension. And both the chi-square and the AIC tests favor the model with a fixed m. But as the values for the AIC test are all very close to each other, we cannot claim that there is a strong evidence for any of these models, right? So I hope it was clear so far. We made these constraints using redshift space distortions on this model, and well, it's not really definitive which model is best. They are very close to each other, even with the model with a free parameter m. All right, so the second part of my talk refers to forecasts with gravitational wave interferometers. And right now we have in operation LIGO Virgo, and but well, maybe not so soon, but in the next decade, in 2030, 2035, maybe it will start in operation, hopefully, LISA. It's a space telescope for space interferometer, better saying. And from 2035, there are plans for the ET telescope to be built. This is still unsure, but it will be very interesting if it's indeed built. And with the hope, what is interesting for cosmology is to look at standard sirens, which are astrophysical events measured both in the electromagnetic spectrum and in gravitational waves with the interferometers. And examples of standard sirens are these neutron star mergers, black hole binaries with accretion disks, and extreme mass ratio in spirals. Now, what we've done for forecasting, to see how gravitational waves in the future can constrain this FFQ model, we constructed catalogs for these 3 experiments. For LIGO, we generated 15 catalogs, each one of them with 50 events, and we are follow the specifications, the expectations that we found in the literature. So in particular, these 2 papers, Baker and Macarena. And then for Lisa, we generated also 15 different catalogs, each with 15 events only. And we picked 3, or we characterized 3 types of catalogs, the very good ones, the median, and the worst catalogs, right? So this is a procedure that was found also in Sperry 2021. And then for the ET catalog, we generated 5 different catalogs, which with 1,000 events, so we expect a huge number of events. Probably this is going to be revised soon enough. But because we have so many events and at low redshift, we see that the catalogs are all very similar to each other. And in the end, for the analysis, we only use one single catalog with 1,000 events. All right. Besides that, we use Supernova 1A data from the Pantheon compilation to constrain essentially omega matter, right? All right. So to construct the catalogs for gravitational waves, we used the specifications we found in the literature for each of these 3 different experiments. So there's a PDF, probability distribution function in redshift for the standard sirens. We pick up a random number for the redshift. We use this PDF, and you get we accept or reject the data point, and then looking at a given redshift, we expected a given error bar for that data point. So this is also specified in these articles. And so we generate a data point with an error bar in the luminosity distance plot, which is essentially the Hubble plot, right? And then using a Gaussian distribution, we shift this data point up or down depending on generating a Gaussian number. With respect to this median value, which is the luminosity distance for our fiducial model, which we are going to use as ΛCDM. ΛCDM is going to be the fiducial model to construct the mock catalogs, and then we compare the FFQ cosmology against the mock catalogs. All right, so that's what we are doing. This is the procedure. So I hope it was clear. You can find more on this in GitHub of José Pedro Ferreira, who was my master student. He's going to defend next week, and so he made a code for all these catalogs for these different missions, and it's in GitHub. You can find it there. You can use it for yourself. All right, and then so these are an example of a catalog for Lisa, and this is what I mean: the worst, the median, and the best catalog using also Pantheon, because Pantheon is important to constrain omega matter. So you have on the left a figure with okay, how are you? All right, so you have the catalog with the data points. We have the different colors, and then so you can immediately see. I'm not sure if it's clear for you. It's a bit small here, but the thing is, we found the trend. The best catalogs, the ones that give us the smallest ellipse in the constraints, are the ones. Sorry, it's the green. Yes, exactly, the green ones. Is the green one, which is the one that have the lower redshift data, right? So low redshift data is very important actually to make constraints on these parameters m, h, and omega matter. And just a quick parenthesis, quick note: this alpha is the same as m that we used before. So from different papers, we used m or alpha, but it's exactly the same thing. It's the same parameter, all right? I hope you remember this. Okay, so the bottom line for this slide is low redshift data is important so that we can have good constraints, all right? High redshift data is also important, but the point is, the problem with the high redshift data is that the error bar is also bigger. So there is an equilibrium here. We want high redshift, of course, but we wish the error bars were smaller to constrain cosmology, because the error bars are larger. We expect error bars are larger. Then there's an equilibrium here. There's a sweet spot on the redshift that we're going to talk about later on, just as a conclusion, because we actually computed what would be the best redshift to look at. If you only had one observation, if you could choose the redshift, what would that be? All right, so this now is a catalog for the ET. Once again, we only use one catalog because the data points are so many. So there are 1,000 data points between 0 and redshift 2. They don't exist yet, and we expect them to exist in the future. All right, so and that's the constraints we obtain. Comparing one with the other, then you can see that, for example, comparing the best LISA catalog with Pantheon and ET, it's clear that ET outperforms LISA. And the question, once again, is that ET has many data points at very low redshift. And LISA, of course, it goes to high redshift, but the error bars become very large, right? So this is the down point. But ET is better, or expected to be better, but it's not. They are comparable. The contours are comparable, I would say. Right, now, can LIGO help? So we have already seen that LISA is not as good as ET, but if we have one universe, and the universe is going to give us, let's say, you can put it this way, one of these catalogs, right? We don't know what it's going to be. We don't know what nature is going to give us. It's going to give us very good data or poorer data. What is the redshift that we're going to find these standard sirens? They are pretty random, right? So if the universe gives us, nature gives us a bad catalog, could we join LISA data with LIGO and get something as comparable to a good LISA catalog or even to ET? So that's what we are doing here. We're comparing the LISA worst catalog, the LISA worst plus LIGO, LISA worst, and the median LIGO, and LISA and the best LIGO catalogs. So what we found is that if you join LISA, a very bad LISA catalog, with a good LIGO Virgo catalog, then we have good constraints. Actually, we have constraints pretty much as good as a good LISA catalog. So this is a bad LISA catalog, right? And then if you have bad LISA catalog with a LIGO, then we have constraints like this, very small constraints. Okay. So this is very interesting. A good catalog can improve LISA constraints. A good LIGO catalog can improve LISA constraints. All right, so here I have a summary table of what we are talking about. Essentially, we are comparing the sizes of these contours, right? The bigger the contour, so less precision we have on the data. If the contours are smaller, which means we can measure this by the error bar on alpha or the M parameter. Remember, it's the same thing. Then if these contours are small, it means that they have a small error bar on alpha. That's how we compare the different catalogs and the constraints. So ET is clearly the best one, has a smaller area, and then LISA best is second place. It comes in second place, and then LISA, the bad catalog for LISA, and then LIGO, very good catalog for LIGO, gives us the third place, and then LISA median and worst come in the last places. All right, so this is interesting. We also compare the relative sizes of these contours, or the error bars, if you don't want to put it like that, and this is the relation we get with each other. So for this second part, these are the conclusions. The Einstein telescope clearly will perform better than LISA. LISA will perform better than LIGO, hopefully. After all, it's a space interferometer. LIGO alone will not be able to constrain this model, but you can obtain different catalogs for LISA and LIGO, and the Einstein telescope catalogs are all very similar. So this is actually, you should put this sentence somewhere else. It doesn't come in as a consequence of the argument, but if you obtain the bad LISA catalog, you can use LIGO to complement the data and obtain good constraints on these parameters. And I didn't discuss this. I just mentioned in past. I didn't show how we calculate this, but I was mentioning before that true, we want low redshifts and you want high redshifts as well. The problem is that at high redshifts, the error bars are typically very large. So if we could only choose one data point and you could choose the redshift, which redshift would that be? and we computed this and we made an estimation that would be at redshift 0.6 for LISA, and z equals 1 for the Einstein telescope. So this is interesting. Of course, we don't know, we cannot choose exactly what the standard sirens will happen, at what redshift I mean, and but we want low redshift for certain. Okay. All right. And now, in the third part of my talk, I'm going to talk about a different model. So going beyond the LCDM background assumption. So we previously we chose an f of q that would still give us a LCDM background, and we're looking at the effects on the evolution of the matter contrast, because there was a modification in that equation of motion, and look at the effect on the gravitational wave propagation, right? Now we're going to look at an FQ model that does not longer require that we obtain a LCDM background. Okay, so this is a model that was proposed by Agnostopoulos, Basilakos, and Saridakis. That's why I'm calling it ABS FQ model. It has this look, right? So FQ is of this nature. So it's q times an exponential. Of course, if lambda is 0, f of q is q, which brings us back to general relativity, right? So they claim, and I'm citing them here, one of the first alternatives to the concordance model that, apart from the fact that it might be preferred by the data, so after the analysis they show that it might be preferred by the data, it does not face the cosmological constant problem since it does not include a hidden cosmological constant inside of q, right? So they argue this, but I disagree with this claim. I think the cosmological constant is there actually. I can see this immediately. Essentially, we have this parameter lambda, and we must relate it with omega matter. They wrote it in the paper actually. Lambda is written in terms of the Lambert function like this with omega matter. How they relate one with the other? So we have the same number of parameters as in omega matter in lambda CDM, right? So omega lambda is related to omega matter because for a flat universe, things have to make sense, right? All right. Now, so this is what we obtained for the Friedmann equation, essentially. This is the Friedmann equation. E is h over h naught, right? In the limit of low redshift, all right? So when E is small, it's close to 1, this is what we obtain. So it's like lambda CDM. So I think this is the hidden cosmological constant. You see, the cosmological constant is somehow here. So you obtain something like lambda CDM, but with a modified omega matter. At large redshifts, we recover exactly lambda CDM, right? So omega matter, and this is the cosmological constant, of course. But so this omega matter, effective log omega matter, is different from this one, all right? So that's the interesting thing here, how you can see this, how you can understand this model. All right, so when you compare, making, once again, mock catalogs using the Pantheon, mock catalogs for LISA, here LISA median, LISA best, and ET, and this is the Pantheon only. Then for lambda CDM, as lambda CDM, I mean, as the Pantheon, as the supernova cannot constrain H, we have this bar in brown color, right? So this is what you obtain. You obtain, supernova allow us to constrain omega matter. And when you obtain the catalogs for the gravitational waves, we have these 3 different catalogs, once again, for LISA, median, best, and ET, right? So they are all, everything matches well because the mock data was constructed having lambda CDM in mind as a fiducial model. So everything is okay within 1 sigma error bars. Now, for the same mock catalogs, now we do the same analysis with the FQ model, this ABS model of dark energy, and then we'll find an inconsistency, right? So the values you obtain with Pantheon and the values obtained on omega matter with the gravitational wave data would be inconsistent. If they are consistent at low redshift, they are inconsistent actually at high redshift using the, because of this, essentially, because of this relation here. Because you have a low redshift, you have this Friedmann equation, and high redshift, you have this Friedmann equation. Okay, essentially, if we find in the future an inconsistency between the omega matter obtained with gravitational waves and omega matter obtained with Pantheon, this would be a suspicion that lambda CDM is okay, because we did these constraints for these mock catalogs for lambda CDM. We could have done the opposite. We could have constructed mock catalogs for LCDM, and we would obtain, if this FQ model is the correct one, we will obtain an inconsistency here and something consistent in here, of course, if this model was the correct one. So we are looking into this, right, for this model, because it doesn't allow exactly for a LCDM limit, then we would expect an inconsistency in the different data using supernova or gravitational wave data. So standard sirens, bottom line, can help to discriminate between these two models of dark energy. All right, so this is what I had to present to you. I hope it was clear. I'm open to questions now, and thank you for listening.
Okay, thank you very much. Okay, any question? พี่กัมพีมีไหมครับ
Okay. Actually, I'm not familiar with the FQ theory, but I would like to ask some question. In the how many degree freedom for gravity in the FQ theory?
Good point. I'm not sure. I would have to look at the paper actually. I'm sorry, I don't know. So in which sense are you? What do you mean? In which sense? Because in f of r you have one more degree of freedom, if I'm not mistaken. Is that correct? What do you mean? So this should be close to f of r, not in f of t. You have one more. You have one more, right? Is that what you mean? Is that I have to look at the papers. I'm not sure.
Okay. And I saw in your paper that FQ gravity will equivalent to GR when FQ equal to Q.
Exactly.
Yes, and this is this mean that FQ gravity can transform to GR or
in f.
which aspect they are equivalent?
So if f of q is q exactly, then you obtain general relativity. So in this paper of the Trinity of Gravity, this is clear. You obtain some boundary terms that we can then neglect, and then we obtain exactly gr. With f of q, I mean we obtain the limit. I mean then it's a different theory, and it's a different theory from gr. With the, I mean, depending on how you write f of q, you can obtain the limit of gr. So that's essentially what the procedure we took, right? The approach we took. We still obtain the gr limit, because when m is 0, you have f of q is q. Yeah.
Okay. And okay. Okay.
Okay. All right.
Last question. The question is
Okay.
quite.
All right. Okay. Yes.
Because actually I not familiar with the forecast the model. If you use the lambda CDM model to generate the catalog for the data, this means that lambda CDM will fit well with the generate data, right? Okay. If you generate some data from lambda CM, Is this mean that lambda CM is the best fit of this data? You get my question?
More or less. Would you repeat that again, please?
Okay. Okay.
No, please
Uh,
repeat. Yes.
okay. In your work, you use the lambda CM to generate your data
Yes.
point, right?
Yes,
And
exactly.
if we use that data point to fit the model, uh, is the best fit model should be lambda CM model or
All right.
what does it
Okay.
mean?
All right. I think I understand. So in the constraints with using current constraints, current data on redshift space distortions, we found the best fit was not lambda CDM, right? It included lambda CDM, but it wasn't lambda CDM as best fit. The difference between the two we saw using the chi-square and the AIC test wasn't concluding. I mean, wasn't you could not really say which one is better than the other one. But in terms of best fit, the best fit was m different from 0, so not lambda CDM. Now using gravitational waves, of course, we don't have data yet. We have one data point right now, and so we constructed mock catalogs for lambda CDM, and in that case, essentially, you can look, but essentially, because lambda CDM, I mean, mock catalogs of lambda CDM, the best fit is lambda CDM, right? So the parameter alpha and parameter omega m are very close, or depending on the catalog, but they are within 1 sigma of the best fit. So different catalogs have a different best fit, of course, but it's all very close to, or all the contours includes lambda CDM. Okay, I mean, because we used mock catalogs for lambda CDM, of course.
Okay. Thank you so much.
All right. Okay. Any question? More question you would like to ask? Okay.
Okay, for me, it would be very basic question because I am out of the field. Uh, I would like to just make sure that I know the concept of like, uh, in order to construct like, the Lagrangian with like the R, the T, and the Q. Like as you said that it came from the affine connection, right? Where the R part, the Ricci scalar, come from like the Christopher symbol part, and the T part is tied to like the torsion tensor, right? And I believe that the T is like the scalar contraction of that torsion, and it
Yes,
would likely tied to like measuring how the space, how much the space twisted, some sort. But I would like to know that the last part of that would be the Q part. Is it tied to like the scaling of the space time? Because uh, there is a picture that you show like the last one.
the length of the
Uh,
vector will change along the path. Yes. Um,
so is that mean that the space got different scaling at each point? I don't know if it's connected to like the conformal transformation of some sort.
yes. Yeah, I would compare it. Maybe I'm not sure if it's correct, but that's what comes to mind. Yes, it's something like a conformal, but it's not the conformal. Yes, it changes the sizes, right? But not the angles, right? So it's something closer to conformal. Yes, I would suppose. Yeah. I mean, I think I agree with you.
Okay.
Any more questions?
Would be interesting to know, to devise an experiment that could tell us what is actually the nature of gravity, if it's which one of these three is correct. But I don't know, if you have any idea, it would be great.
Okay. Well, let me ask last question about your FQ function. Actually, you take it in the exponential function form, right?
Well, that's not my model. That one is not my model anymore. But yes, it's the ABS
Yeah,
model.
yeah. Just would like to know the motivation why it has to be the exponential function form. Can it be something else?
In principle, can be anything, of course.
Or it can be anything, right?
In principle, can be anything. I mean, I in my research, the model I proposed,
Mm-hmm.
I mean, actually, it wasn't. I will propose this. I mean, it was actually in Jimenez, Beltran Jimenez, and Lavinia and Tommy Visto model is the FQ cosmology. I think that's the title of that paper. They proposed. They noticed that the Friedman equation allowed for this form of f of q and you obtain a lambda CDM still, or you still obtain the usual Friedman equation. And so I thought that was interesting once again, because I mean, if we establish the background, then let's look at the perturbations that would be helpful to discriminate between different models. But the other model, the FQ model with an exponential, this was from other authors. So Agnostopoulos, Basilakos, and Saridakis, and I suppose I suppose this was a way to obtain dark energy without an explicit component for dark matter, for dark energy. But I mean, once again, I think it's hidden there, because if you have the exponential, it's the exponential that gives us dark energy essentially, because this lambda that's in the exponent turns out to be omega lambda, right?
Okay. All right. Okay.
It's a cute trick, I think, but I think that's the motivation.
Okay. All right. Thank you very much. Okay. Okay. Oh, another question. I think the last one.
Another question. Comparing to the Einstein field equation, where the source term, I mean the source of the curvature is like is like the energy and the mass, like the energy momentum tensor, right? In but comparing for the Q, what is the source? I mean what I mean comparing to the Q form of the Einstein field equation, maybe possibly what is the source of the Q, which is I'm not sure. Maybe
I mean, but you still have matter there. You still have matter in the action. You can still define an energy momentum tensor. But that's the source in the Einstein equation. Is still similar, right? To the left hand side, it comes from varying the action with respect to the metric and to the affine connection, like we do in the f of r series or in f of t, right? But the only thing is that now we have g mu and lambda. So the gamma has the defined connection. They are different entities, right? In this case, they are different objects. A bit like the Palatini, right? Palatini approach. Did I answer your question? Or?
yeah, but that is have like the physical interpretation of that. Like you say that it like form like the derivative of the of the metric the same way as the energy momentum tensor, right? But using like the different kind of affine connection. Is is that what you mean?
We use it. We vary with respect to one, to the affine connection, and to the metric. Right? You have to do. We don't relate one with the other. It's like like in Palatini, as I was saying. but I'm not sure if I have the feeling I'm not answering your question, or I don't understand your question. So not sure what. Well, if I'm understanding your question, as because the source term is still the varying the Lagrangian with respect to the metric, and that means the energy momentum tensor. That's how we get the energy momentum tensor has. That's the usual thing as we use for general relativity with interpreting as a curvature of space-time.
Thank
Are you
you.
okay? Yeah.
All right. Okay. I think it's about time. So I would like to thank Professor Nunes again for this for giving us a very interesting talk. Okay. Let's join me to thank. Yeah.
Thank you for having me. Thank you very much. I had a really
And
great time in Pizzano Log some years ago.
all
It's,
right. Okay. Hope you
it's,
come again soon.
yeah, no, I still have it here. I cherish my mug.
All
Yeah,
right.
yeah.
Okay.
It's,
All right. Ah, right. Okay.
it was
Couple. Yes.
yes,
Couple
great
school.
time. Yeah.
Okay. All right. Okay. Anyway, before we go, who watching online, you can complete the survey form that actually provide um, that link on the screen actually. But for the people in this room, you can complete the survey form with a hard copy. And so with let well let's finish the talk for today, and then stay tuned for the next if colloquium for next month. We'll see you again soon. Bye. Thank you very much.
Okay. Bye bye. Take care. Bye.